Okay, folks. Basically, we will start the Holder inequality, the proof of the Holder inequality, and a key inequality that is used here is Young inequality, which is basically this inequality here. And it tells you that if you have alpha and beta are two positive numbers, then if you raise alpha to the lambda, beta to the 1 minus lambda, and lambda is living between 0 and 1, then this is less than or equal to lambda alpha plus 1 minus lambda beta. And in fact, you can basically extend this to cases in which some of the variables are equal to 0. You should just avoid the cases in which like you have 0 to the power 0 because this is not defined. But otherwise, actually, you can have some of your variables equal to 0. Okay, so you can again prove this using calculus as in the notes, or you can basically use the concavity of the logarithmic function to like prove this statement in maybe a couple of lines. Okay, so this will be our starting point, and we have two vectors living in the n-dimensional complex space, vector x and vector y. Each one has n components. Typically, basically those are complex numbers, and basically let's take the case that each one of those vectors is not the all zero vector of the n-dimensional complex space. So here is the trick. So here is how we'll use the Young's inequality to prove Holder inequality. Okay. So we will basically define alpha. We will take alpha here to be the absolute value of xj. So that's the jth component of xj. So you take x of j. It's generally a complex number. Then you take its magnitude. You raise it to the power p. Okay. And then you divide by the bth norm of vector x raised to the power p. Okay, so remember that basically this is the bth norm, the LB norm of vector b raised to the power p, because basically the vector norm, you will take x of j, raise each guy, the magnitude of each guy to the power p, then you do a sum over the components of the vector, and then for the norm you will take the bth root, but here we don't take the root, so this is the bth power of the LB norm of vector x. And beta is defined similarly, but it involves vector y. So here we have the components of vector y, and we raise to the power q. Okay, and we raise it to the power q. Note the following, that if you want to make use of Young's inequality, then here alpha is raised to the power lambda, beta is raised to the power 1 minus lambda. So these powers are not arbitrary. Their sum is equal to 1, and lambda is living between 0 and 1, right? So basically this is reflected here. If I raise this to the power, this will be raised to the power lambda, and this will be raised to the power 1 minus lambda. So we will take lambda to be 1 over b. So b greater than 1, and lambda is 1 over b. Now, if this is lambda, then the other power, which is 1 minus lambda, is 1 over q. So it means that those powers p and q again are not arbitrary. If you specify one of them, then the other is specified. And since lambda is 1 over b, you can write your equation as such. So the relationship between p and q is that 1 over p plus 1 over q is equal to 1. So the Holder's inequality, it involves the LP norm of vector x and the LQ norm of vector y, again so long as 1 over p plus 1 over q is equal to 1. So just now put your basically alpha and beta. So we will take this alpha and raise it to the power lambda, and lambda is 1 over b. So when you raise this thing to the power 1 over b, then those powers become 1, and you get this stuff. So this is alpha to the power lambda, where lambda is 1 over p. Now this is to the power q. You raise it to the power 1 minus lambda, and 1 minus lambda is 1 over q. Then again the q here those guys are raised to the power q, now they are raised to the power 1. So this is basically alpha to the lambda, and then beta to the power 1 minus lambda, with lambda equal to 1 over p, and 1 minus lambda equal to 1 over q, and so 1 over p plus 1 over over q must be equal to 1. And this should be less than or equal to this side here. So now we have every parameter here is specified. We know that this lambda is 1 over p, this 1 minus lambda is 1 over q, and then alpha and beta are given in terms of the components of vector x and vector y respectively, and so you just put everything here. Okay, so this is an application of Young's inequality. Okay, sort of to the components of vector x and vector y. Now what you do is that you sum. Okay, so you take both. So again, this inequality is true. So this is true for j equals 0 and 1 up to the last component in each vector, which is n minus 1. And you can simply sum those inequalities. So you sum from 0 to n minus 1. Okay, and when you do so, basically this is what you get on the left-hand side. On the right-hand side, if you sum this, then you get the bth power of the LP norm of vector x. And when you sum this over the components of vector y, you get the LQ norm raised to the power q. But here we have this in the denominator, and here we have that in the denominator, and so basically we get ones, and we are left with 1 over p plus 1 over q, which again is equal to 1. Now you can multiply both sides by basically this quantity here, which is assumed to be positive because we excluded the case that vector x is the all-zero vector or vector y is the all-zero vector, and so this is the inequality that we are after. Okay, so if you sum the product of magnitudes of these two vectors x and y, you get something that is always upper bounded by the LP norm of vector x, the LQ norm of vector y, where 1 over p plus 1 over q is equal to 1. And you can show that, for example, that this expression is true if one of the vectors is the all-zero vector. So we excluded this case initially, right, because of how we define alpha and beta. We define them by dividing over the norm, and if the vector is all zero vector, then its norm is 0, and we are in trouble because we are dividing by 0. So we simply exclude those cases while doing the derivation so that we have the liberty of having them in the denominators, but then after reaching the final result here, then we say, okay, you know, if x is the all-zero vector, you know, is this inequality satisfied? It is satisfied, right? Because if x is the all-zero vector, for example, then we know that from the properties of norms, a norm is 0 if and only if we are talking about the all-zero vector. So basically, if x is the all-zero vector, this guy will be 0, and all the components of x will be 0, and so this summation will also be 0. So 0 less than or equal to 0. That's a correct mathematical statement. Okay, so actually this is true. This is true for basically the situation which we have one or the two guys are the all-zero vector, and also you can go like to the boundary cases. So if you set p equals 1, which means that q is infinity, or vice versa, again you get something that is true, and you can verify this as a special case if you wish. Okay. Now, note that if you take the inner product of two vectors, x Hermitian y, okay, so the Hermitian of a vector, so the vector is like this. It is, the default is equal, so if I say the word vector in this course, then the default is that it is a column vector. And so this is vector x here to xn minus 1. Its Hermitian is simply, it's a transpose, so you convert it into a row vector, but then you also take the complex conjugate of each of the elements. So basically this is x Hermitian, row vector. And if you multiply this with vector y, okay, so this is vector y, then you simply multiply the the components as you do in matrix multiplication. So this product will be this guy times this guy plus this guy times this guy and so forth. So you get this summation here. Okay, and by the triangle inequality, we know that the magnitude of a sum is less than or equal to the sum of magnitudes. And so this is less than or equal to the sum of the magnitudes, which is proven to be less than or equal to the product of the LP norm of vector x and the LQ norm of vector y. So we can basically write down, so this is Holder's inequality here. Okay, so basically you can start it from the inner product, or you can start it from the sum of the magnitudes of each component in vector x and vector y. In all cases, the magnitude of the inner product of vectors x Hermitian y, and of course, this quantity is equal to the magnitude of y Hermitian x, right? Because y Hermitian x is just the complex conjugate of x Hermitian y, and the magnitude of a complex number is the same as the magnitude of its complex conjugate. So the magnitude of y Hermitian x or x Hermitian y, okay, but this summation is basically x Hermitian y, and you can apply the triangle inequality and say that this summation is upper bounded by the sum of the magnitudes, and the magnitude of a product of two complex numbers basically is the product of magnitudes. And then using Young's inequality, the first part, we basically prove that this is upper bounded by this product of the LP norm of vector x, LQ norm of vector y. And now you can basically trace when those inequalities can be satisfied with strict equality. So for example, for the triangle inequality, remember, it is satisfied with equality if all the complex quantities, they have the same angle, the same argument. And for Holder's inequality, it is derived using Young's inequality. And so basically you can show that basically this inequality is true. This inequality is true as an equality. It's true as an equality. Okay, given some condition, and this is explained in detail in the notes. I will just here mention the basically the final sort of result, that the magnitude of the inner product is basically the product of these two norms, again, not arbitrary norms, but with 1 over p plus 1 over q equal 1, if and only if you have this relationship between the components of vector y and the components of vector x. Okay, so again, this is true for j living between 0 to n minus 1 if we count the components starting from 0 to n minus 1. So you can find basically that if you look here, you will find that y of j, you can choose here any arbitrary complex number, then e to the I, and you should use here the angle of xj, okay, and then you have the magnitude of xj raised to the power p over q. Okay, and again, this may seem like mysterious, but it is simply obtained by combining the condition for equality for the triangle inequality and the condition for equality in Young's inequality, which, as I said, is explained in the notes, because this is driven using like sort of elementary calculus. Okay, so if you are interested, you can basically read it there. Okay. Now, the Cauchy-Schwarz inequality is a special case. It is the case in which basically P is equal to Q is equal to 1 is equal to 2, right? Because 1 over 2 plus 1 over 2 is 1. So basically this satisfies our condition. And in that case, if you go to the condition of equality, you will find that it simplifies it as such. So now P is equal to Q. So in a general Holder inequality, we have here P over Q, but now this is just to the power 1. So Yj should be some complex number that does not depend on the index j. This is the jth component of Y. So it is some complex number e to the I, and then multiplied by the angle of xj multiplied by the magnitude of xj. So what are those guys together? So this is the magnitude of xj, and this is the phase term, e to the I, the angle. And so these two guys together are nothing but the complex quantity xj. So it means that for the Cauchy-Schwarz inequality, you get equality if and only if each component in vector y is some complex constant multiplied by the respective component in vector x. In other words, you can write it as that y, vector y, is equal to some complex constant multiplied by x. So it is only in this case, it's only, basically it's an if and only if statement. If y is some complex constant multiplied by vector x, then the Cauchy-Schwarz inequality will be satisfied with equality, right? So the Cauchy-Schwarz inequality, here it is. It's missing here the magnitude. So the magnitude, now again you just replace p by 2 and you replace q by 2, and so this is the Cauchy-Schwarz inequality. So if in the short form of it is that the magnitude of x Hermitian y is less than or equal to the L2 norm of x multiplied by the L2 norm of y. Very, very important and very, very useful. Okay, so the magnitude of the inner product is less than or equal to the L2 norm of vector x multiplied by the L2 norm of vector y, and basically this is the L2 norm of vector x, and that is the L2 norm of vector y. Now we have equality if and only if y is some constant, some complex number multiplied by x, which means that if we use like the language of linear algebra, that x and y are linearly dependent vectors, right? Because this is the meaning that two vectors are linearly dependent. It means that one of them is just a constant multiplied by the other. Okay, so it is only in this case that we get an equality. Otherwise, the Cauchy-Schwarz inequality is satisfied with strict inequality. Okay. Cauchy-Schwarz inequality and the Holder inequality are also valid for integrals. Okay, and so basically for sums. Okay, and so those are other forms that are very useful. Okay, and we will see them applied in this course. Okay, so if you basically assume that you have an infinite dimensional vector, so like you have a sequence now, rather than having just a finite dimensional vector, you have a sequence. It's valid, So basically, this is true. And if you have an integral, this is also true, right? So this is basically the Cauchy-Schwarz inequality. Again, it means that you take the magnitude. Okay, so I can write it in other forms. So if you take the j from 0 or 1, to infinity of aj, bj. Right? So this is always upper bounded by the square root. So square root, it's because it's in the definition of the L2 norm. And then you have the summation g from 0 to infinity, the magnitude of aj squared. Okay, and this is multiplied by the magnitude of bj squared. Okay, and you have equality if and only if basically bj is some c which does not depend on aj conjugate in our case here, right? So you can write it like this. It's like I replaced x by a and y conjugate by b. So here we get equality if y is some complex constant multiplied, if yj is some complex constant multiplied by xj. So here we will get equality if bj is equal to c multiplied by aj conjugate. So you can play this game, that you can basically apply this to aj and this thing here bj with its conjugate. Okay, so if you see a summation without conjugates, no problem. You can still go for the Cauchy-Schwarz inequality. Okay, so don't make this confuse you. You can do, the only thing is that when you write down the condition for equality now, So if it's summation AJ BJ, now you should say that BJ is C A conjugate J, or you can put the conjugate on the other side. Okay, things also are applicable to integrals. Okay, so this is one form, and you can play the same game again. Say that integral of z of t, h of t dt is less than, or magnitude, of course, is less than or equal to square root then the integral of magnitude of z of t squared dt magnitude of h of t squared dt. And you get equality here if h of t is equal to a constant z conjugate of t now. Okay, and this should be true for integrals if you want like to be accurate. You do not need this to be true for every t, right? You need this to be true. So here you need this to be true for every j in the case of sums and vectors, but in the case of integrals you need this to be true almost everywhere, right? Because if this relation is violated basically on a set of measure 0, then the integrals don't care, right? So remember that basically the integrals are insensitive. They are blind to those things that you may the perturbations that you may do on a set of measure 0, right? So so here basically, yes, you can violate this so long as you do the violations on a set of measure 0, then you are fine and you will get an equality here. Okay, so those are very important inequalities and we will make use of them later. Okay, let's talk further about the relationship between the norms. Let's go back to the finite dimensional space where things are like sort of relatively easy to prove and handle. So we want to prove basically this statement here. So I mean, a question that comes in mind, like, if you have a vector and you compute it like its LP norm and its LQ norm where Q is less than B, is there a relationship, right? Or sometimes the LB norm of a vector is greater than the LQ norm, sometimes it's the other way around. It turns out that there is a pattern. Okay, it turns out that if you compute the the norms, that basically there are relations that basically that are sort of true. So if Q is less than B, and actually this is true even if we define things from 0, right? But for those guys to be actual norms, mathematical norms, you should start from 1, right? But it turns out that actually this relation, so if you define this thing here, okay, x of j to the power p, j from 0 to n minus 1, and then you raise it to the power 1 over p, now you can basically make b here equal to 0.5. Okay, in that case, this expression makes sense. I mean, you can compute this expression, but it is not a norm. It is not a norm, and you can show that basically you will violate the triangle inequality. Okay, so for these things to be true norms, true norms, they should satisfy a number of properties, including the triangle inequality. Then they should be greater than or equal to 1. But actually, if you just forget that these are norms and take their definitions as sums, then actually you can extend this to all the way to 0. Okay, so this is just a technicality. We will typically be interested on those guys as norms, so our interest will be like something like this: Q greater than or equal to 1 less than B. But the most important thing here is Q is less than B. So here is the claim: if you take any arbitrary vector in the n-dimensional space, right, and if you compute basically the LQ norm and the Q is less than B, then the LQ norm is greater than or equal to the LB norm. Okay, so this is always true. It will always be the case that, for example, let's give you an example, that the L2 norm of a vector, right? So here I'm using 2 for P, is always less than or equal to the L1 norm of a vector. It's always less than or equal to the L1 norm of a vector, okay? And there is a nice relationship that the LQ norm itself is less than the LP norm, but multiplied by this quantity here, which is the you mean when does it satisfied with equality? Yes, it can be satisfied with equality if basically the vector has all its components, only one non-zero component. Then basically these norms will be exactly equal. Okay. Okay. So this. Now let's do a proof. Okay, this is a very nice property, by the way. And it tells you how the different norms are like linked to one another, and this will explain to you like something like if you are studying, let's say, multivariate calculus or something, and you have a definition, like a definition of a sequence of vectors. Okay, so you'll find that the definition of a sequence of vectors, a norm is used in the definition, and sometimes it is not specified what type of norm people are talking about. So it is the LP norm, LQ norm, maybe it's another type of norm. And the reason is that you can use any type of norms. Norms have some sort of equivalence between them. Okay, and so in many applications actually you can exchange them. You will get different results, but like when you take limits and so on, you get the exact same result. Okay, so let's prove this result here. It's actually two inequalities. So we need to prove this guy and to prove that guy. So this inequality and that inequality. Okay. Just as a reminder, if you have a number living between 0 and 1, now if you take this number and raise it to higher and higher powers, then this number gets smaller and smaller. Like if you take 1/2 to the power 2, it's 1/4, to the power 3, it's 1/8, and so on. And if a number is greater than 1 and you raise it to higher powers, then it becomes larger and larger. Okay, so just keep this in mind. Okay, of course, if basically the trivial case, what is called the trivial case, if basically vector x is the all zero vector, right? If vector x is the all zero vector, then all norms are equal. So that's another trivial case in which the inequalities are satisfied with equality, in which like you set every component in the vector equal to 0, and in that case, you will have 0 less than or equal to 0 less than or equal to 0, and so that's trivially satisfied. So we will basically focus on the case in which the vector is not the all zero vector, and so its L infinity norm is greater than 0. So remember what was the L infinity norm? So the L infinity norm, in the finite case, you take the maximum, so j in 0, 1, 2, n minus 1, okay, and then you take the maximum magnitude, and this will be the L infinity norm. Okay, of course, if the vector is the all zero vector, all components will be 0, and this guy will be 0, but now we will assume that there is at least one component that is non-zero. Okay, so here is what we do. Okay, and so we'll do this. So I will take magnitude of x of j. Okay, so this is the jth component in vector x, and I will divide this by the L infinity norm of vector x, which is defined as such. Now, what do you think about this alone? This term alone is less than or equal to 1. So this guy alone is less than or equal to 1 by definition, right? Because the L infinity norm is the maximum. The L infinity norm here is the maximum guy, the maximum magnitude. So definitely if you take the magnitude of x of j, then and you divide it by the L infinity norm of the vector, you will get something that is less than or equal to 1, and you will get a 1 if j basically is the index of the element with the maximum magnitude living inside the vector. Okay, so this is less than or equal to 1. So what if we basically sum? Okay, so we take this, raise it to the power p first. Okay, so we'll raise it to the power p. Okay, so if you have something less than or equal to 1, you raise it to the power p, actually it gets smaller. If it's 1, it remains 1. If it's a fraction between 0 and 1, then it gets smaller as, or if it's 0, of course, it remains 0. If it's a fraction between 0 and 1, it gets smaller, but the idea is that it remains less than or equal to 1. Then you sum, okay, j from 0 to n minus 1. So you sum over all the components in the vector, right? So now, what do you get? So what is this quantity here? Now, basically this quantity, what is, basically the denominator here is just a constant, right? So this is basically the x infinity norm, and when you do the sum, you will get the LP norm, and then everything is raised to the power p. Everything is raised to the power p, okay, like this, okay? So you get, so basically this is the summation written in norm form. It's basically the LP norm divided by the L infinity norm, and this is greater than, this is basically this one, the LP norm divided by the L infinity norm, okay, is now something that is greater than or equal to 1. And why is this the case? Again, so each component here, the magnitude of x of j divided by the L infinity norm is less than or equal to 1. But one of those guys is 1. Exactly. One of those guys is 1. That's exactly the reason why basically when you sum, you get something that is greater than or equal to 1. Okay, so this is basically the the observations needed to proceed. Okay. So here they are written like an inequality form. So this summation here, we are summing guys that those guys, each guy is less than or equal to, 1, right? But the summation is greater than or equal to 1 because we have 1 plus non-negative stuff. Okay, 1 plus non-negative stuff. So, but each term here is a number between 0 and 1 raised to the power p. Okay, so we have xj. Okay, let me write it like this. And here is the x infinity norm. Okay, and I will repeat it. And x infinity norm. So if this is raised to the power p, and if this is raised to the power q, what is the relationship? Let's remember our basically relationship that q is less than b. B is the higher number. So each term here is a number between 0 and 1. So if you raise it to a higher power, which is p, you basically make it smaller, right? Again, so this is the observation that if you have a fraction, or number between 0 and 1, then you raise it to higher powers, it gets smaller and smaller. Since q is less than b, then basically this guy is less than or equal to this guy here. Okay, so this is the inequality that we have. Okay, so again, it is like sort of a couple of stories just told on one line. So again, each term, if you look at each term is less than or equal to 1. Raising it to p, which is higher than q, will basically lead to an to be less than if it's raised to the power q. And in all cases, if you sum over the components, you get something that is greater than or equal to 1, because basically in each of those sums, it's 1 plus something, okay? And so this is what we have here, okay? So from this, you just use the definition. It means, 1 is less than or equal to, this is, if you apply this summation to the numerator, this is the LP norm raised to the power p, and the summation applied to the numerator, it's the LQ norm raised to the power q. Okay, so now what you do is that you raise everything to the power 1 over p. You take the b fruit of all the sides, all the sides are basically positive numbers, and so you take you raise each term here to the power 1 over b. 1 remains 1. This becomes the LP norm divided by the L infinity norm, and this basically becomes the LQ norm divided by the L infinity norm, and now it is raised to the power Q over P. Again, the summation itself, this guy, each one is greater than or equal to 1. Okay, so each one is greater than or equal to 1. So here, basically, this term is raised to the power Q over P. It's a number that is greater than 1. It's raised to the power Q over P, which is a number, that is less than 1 because Q is less than B. So definitely this is less than or equal to, if I take the same number, which is greater than or equal to 1, and raise it to the power 1, right? Because you are increasing the power. If you increase the power and the number itself is 1 or more, then basically you have this inequality. Okay, so we are done. You simply take this with that, and you multiply all sides by the L infinity norm of vector x, and this is what you get. So the L infinity norm is like the smallest guy among the LP norms, and basically it is less than or equal to the LP norm, less than or equal to the LQ norm. And again, this may be extended to 0, but I mean, just note that for those to be actual norms, you will have to be greater than, Q have to be greater than or equal to 1. Okay, so this is the first inequality. What about the second inequality, which is that you can take the LQ norm, the LP norm, and you have an inequality, but you need, of course, to add this factor. So here our friend will be Holder's inequality. Okay, so we can apply Holder's inequality, and here is how we do it. We will take the summation g from 0 to n minus 1 x of j to the power q. Okay. And remember, the Holder inequality is a summation involving like two things, right? And it's always good to keep in mind that you can make one of those things 1, the number 1, right? So you have summation j from 0 to n minus 1 magnitude x of j raised to the power q. Okay, so this will be our starting point. So what is this thing? It is basically the LQ norm, right, raised to the power q, because we do not take the qth root. So basically this will be the LQ norm raised to the power q, right? So this is like we are summing like one sequence, or the components of one vector, but you can think of this as a summation j from 0 to n minus 1 x of j to the power q, and each guy here is multiplied by 1. Okay, so what is the Holder inequality telling us? Because we are using P and Q already in our proof, let's apply the Holder inequality with R and S. Okay, so what will be the Holder inequality? Okay, remember, if you have, let me write it using like AJ and BJ. So if you have AJ, BJ, and those are non-negative. Okay, so this is less than or equal to let's here use R and S, the LR norm of vector A, the LS norm of vector B, and again, these two norms are not arbitrary. We need to choose basically R to be greater than or equal to 1, S greater than or equal to 1, and 1 over R plus 1 over S should be equal to 1. Okay, so we'll apply also here. Holder inequality is basically what is needed to basically prove the other inequality. So we'll apply it with R and S. And so what are our like two guys? Again, we will make explicit that there is a 1 here. And so according to Holder inequality, so we will take the first guys here, right? And we compute the LR norm. So what does it mean? LR norm, it means that we will take those guys, so each is the magnitude of x of j raised to the power q, and we raise everything to the power r, because we are computing the LR norm. And then we sum, and after we sum, we raise to the power 1 over r. And then we have basically the LS norm. So this is the LS norm of the all one vector. Again, so here it's not there, but you know, any number can be thought of as the number multiplied by 1. And so this is ones, all ones. Each one is raised to the power s because we are computing the LS norm. We do a summation and then we raise things to the power 1 over s. Okay, so this is Holder inequality. And now, of course, 1 to the power s is just 1. And if you sum 1 n times, right, because the summation goes from 0 to big N minus 1, so we have big N terms here, and so the sum will be big N. Okay, the sum will be big N. And what we will do is that we will make a strategic choice for R and S. So we will choose R to basically be P over Q. Remember that this is a quantity that P over Q is greater than 1. In our proof, Q is less than B. So we will choose R to be equal to P over Q. Okay, and you can guess why actually we are doing this. Now, if you choose R to be P over Q, look here. Okay, look here. This now will replace the qth power by the pth power, and so you will have something, you know, so on the left hand side we have the LQ norm, and now you have the LP norm on the right hand side. So again, this trick is because we want to prove this thing, so you know, this part of the inequality. So we have Q here, B here, and so you start with the LQ norm, right? And then you apply Holder with basically sort of a general powers R and S, and then you basically say, oh, we will choose R to be equal to P over Q, so that now we get the LP norm of vector X. And of course, if you do so, then S is fixed, right? Because 1 over R plus 1 over S is equal to 1. So once you specify the R as P over Q, then S is now fixed. And you can now write everything in terms of P and Q. And this will give us the inequality that we are after. Okay, so this is basically the inequality for the LP norms. And if we have basically infinite dimensional vectors, so if we have something like sequences, well, then this n, it's like we are taking the limit as big N goes to infinity. So basically this side here will explode to infinity, right? So we will have the first part will remain, okay, and then this will be less than or equal to infinity, which is like sort of a trivial statement, okay? So you can take the limit as n goes to infinity, and things will be, you know, true. So this is true even for sequences or basically infinite dimensional vectors. It's always true that the LP norm is less than or equal to the LQ norm so long as P is greater than Q. So what does this mean? Okay, so let's like review what I said in the previous lecture regarding the LP sequences. So we say, or let's call them another name, the LR sequences. So what are the LR sequences? So those are sequences for which if you go and compute the LR norm, then you get a finite number. So basically this means that for the sequence, if you compute the rth norm, then you get something that is finite. Then you say that basically this sequence is part of the so-called the LR space of sequences. So those are the sequences, again, with a finite LR norm. And again, we don't have this issue in finite dimension. In finite dimension, you are basically the sums involved in the computation of norms are finite sums. And if you are summing a finite, basically a finite number of finite quantities, you are guaranteed to get something that is finite. The problem is that when you allow sequences or infinite dimensional vectors, then your sum becomes an infinite sum, and there is a possibility that you go and hit plus infinity, right? So maybe your sum will converge, but converge to plus infinity rather than to a finite number. So this case, of course, is not in the, we do not encounter this in the finite case. Okay, so so what does this inequality tell us? Okay, it tells us that suppose that so again, let me write it here. Q is less than P. Suppose that X and it's a sequence or infinite dimensional vector is an LQ. So again, the meaning of this statement, okay, so this is equivalent to saying that the LQ norm is of this sequence, or you can say sequence, you can say infinite dimensional vector, and of course in this course you can say it's a discrete time signal. So for this is finite. But we know that this is true. So for P that is greater than Q, the LP norm is less than or equal to the LQ norm, right? So if this guy is finite, you are guaranteed that this guy is finite. Okay, so this is by definition. So this is my starting point. Suppose that you are dealing with a discrete time signal with an LQ norm that is finite. Then if you go and compute the LP norm, then you are guaranteed also to get a finite result, because the LP norm is upper bounded by the LQ norm, which is finite. So the LP norm is finite, thus X also lives in LP. In other words, that if you have a sequence that is LQ, it is guaranteed to be an LB sequence. Okay, so if you have sort of a Venn diagram, so if these are the LP sequences, so this box contains all sequences basically that have a finite LP norm. Okay, if P is greater than Q, okay, so the LQ sequences are here. Okay, so these are the LQ sequences. So LQ sequences are basically the sequences for which the LQ norm is finite. And again, because of the inequality we have just proved, if a sequence or an infinite dimensional vector has an LQ norm that is finite, it is guaranteed to have an LP norm that is finite. And again, don't forget the relationship between P and Q. Q is strictly less than so Q is less than Q. Oh, nonsense. Q is less than B. Okay. So so this is like the Venn diagram of this inclusion here, and so this is called the nested property of LP sequences. Nested property of LP sequences or discrete time signals. Okay, so if we focus on the guys that we are typically interested in, so so for example, this is I can have 3 boxes like this. So suppose that you have the L1 sequences, so those are basically the sequences that are basically whose L1 norm is finite. So those are called, absolute summable sequences. Now, if you have a guy that is L1, then it is guaranteed to be L2. Okay, it is guaranteed to be L2, and L2 sequences are those sequences that we call square summable, right? And those guys are a subset of L infinity. So those are sequences for which the L infinity norm is bounded. So those are just the bounded sequences. Okay, sequences that are bounded. Okay, and so each space is living in the, so long as you increase from 1 to 2 to infinity, okay, then you have this nested property. So this is the nested property of basically the LP spaces of sequences. Okay, and here's like a claim. So I'm drawing it like this. So I am like sort of presuming that there are sequences that are L2 but not L1 sequences. So basically, this is the L1 sequences are a proper subset of the L2 sequence. So each guy here is guaranteed to be, each absolute summable sequence is guaranteed to be square summable, but the opposite is not true. And just think about this sequence. Okay, so sequence, let's say x of 0 is 0, x of 1 is 1, x of 2 is 1/2, x of 3 is 1/3, x of 4 is 1/4, and so on, right? So what is the L1 norm of this sequence? Well, it's the harmonic series. Okay, so so basically the L1 norm is infinity. Okay, so the L1 norm is infinity. But what about the L2 norm? What about so basically this sequence, okay, not in the L1 space, because the L1 norm is not finite. It is plus infinity, because basically if you take the magnitudes of those guys and sum them, then you get something that is infinity. So it's not in the L1 space, but it is in the L2 space, okay, right? Because what is the L2 norm of this sequence? The L2 norm squared of this sequence will be 1 plus, 1/2 squared plus 1/3 squared, and so on. So basically this is the famous sum, okay, of 1/n squared, which is pi squared over 6, which is a finite number. So basically this sequence here, so basically our sequence here is in the L2 space, because the L2 norm is a finite number. Okay, so you can come up with L2 sequences. So this sequence is like a point that's here. It's a sequence that has a finite L2 norm, but it's not an L1 sequence, right? Because if you attempt to compute its L1 norm, you will simply get infinity, right? So basically, L1 space of sequences is a proper subset of the L2 space, and so on. Okay. Now, what about sequences? What about functions? What about continuous time series? So what about the LQ and LB spaces? So remember, for example, what are the L? So this is big L. Those are the guys for which something like this, and you define it over some basically subset of R. So let's have LPS, and so this is S. So it's P, so I should raise this to the power P. So if this guy is finite, if this integral is finite, then we say that our function or continuous time signal is LP, big LP, okay? And now, so what is the relationship between those guys if Q is less than P? So let's say that Q is 1 and P is 2. Do we have, this inequality satisfied? And the answer is no. Okay, so basically going from, vectors, even like infinite dimensional vectors, to basically functions, to continuous time signals, the story becomes different. And so basically, how are these guys related? If there is any relationship between them, this will be basically an exercise, or it's actually not an exercise, it's a problem that you will have to solve in homework 2. So in homework 2, there is a problem in which you will simply, play with basically those guys. So you will find that, things are a bit more complicated than for the case of vectors and sequences. Okay? Okay, so of course we are not done with with mathematical review. There are several other things, but we will discuss them as we encounter them during this course. So let's now jump to what you can say the first topic here, in signals and systems course, and it is the classification of signals and systems. Okay, classification of, and we start with classification of signals. Okay, and when you classify signals, there is, a number of ways in which you can do this classification. And so the first basically way of classifying signals is periodic versus aperiodic. A periodic versus aperiodic. It's useful, and we will see that, for example, for periodic sequences, you can define the Fourier series and so on. Okay, so this is the first time. Then, we will take other types, or other types of classification, power signals, energy signals, and so on. So there are several ways of classifying signals. Our focus today will be on, periodic versus aperiodic. Okay, and we will start actually with the periodic and aperiodic continuous time signals. Okay. So let's remind ourselves what is the definition of a signal or being periodic. So a signal is periodic, okay, if you can find a big T that is not zero, such that for every small t that is real, x of small t plus big T is equal to x of t. So x of t should be equal to x of t plus big T for every real t. Okay, so now we exclude the case of zero because it's the trivial case, right? If you put big T equal to zero, then we know that x of t is equal to x of t, right? So there is nothing like sort of interesting if big T is equal to zero. That's like sort of obviously true. So if you can find a big T that is not zero, such that this equality is satisfied for every small t, then we say that our signal is periodic. If this is violated at even one single value of a small t, then we say that our signal is not periodic, or we say that it is aperiodic. Okay, so a signal that is aperiodic is simply that it's a signal that does not satisfy this thing. So it's a binary classification. So there is a definition for periodicity, and if basically this definition is violated in any sense, then basically your signal is not periodic, or it is aperiodic. Okay, so a T-periodic signal, again, it's a signal for which you can find a non-zero big T such that this equality here is satisfied. Now, suppose that you have a signal for which this is satisfied. So there is a non-zero big T for which you know that this is true for every small t. Then actually you can show that this will be, so if this is true, then x of t is equal to x of n plus small n big T for every t in R. So if this is true for some non-zero big T, it will be true for all integer multiples of big T. So n here is an integer. So it will be true. If it's true for some big T, again, if you replace this big T by minus big T, or you replace it by 2 times big T or 17 times big T, okay, so any integer multiple will actually satisfy this equation for you. Okay, so let's, for example, take this. What if you have x of t plus 2 big T? Well, x of t plus 2 big T, you can think of it as x of t plus big T plus big T. So what is this equality telling you? X of something is equal to x of that same thing plus big T. So x of something plus big T is equal to x and then this very thing, right? Because this is, so if this is satisfied, then you can go from here to there. X of something, here it's just small t plus big T, plus big T is equal to x of t plus big T. But this is equal to x of t from this equation here. So right, so x of t plus 2 big T is equal to x of t. Okay, and so on and so forth. You can show it if you replace big T by minus big T, and actually it is true for all integer multiples. Okay, so basically if big T is called the period, so this means what? If big T is a period for a signal, if big T is a period for a signal, then all the non-zero integer multiples of big T are also valid periods of the signal. Okay, so note that you may say, that I'm allowing the period to be expressed as a negative number. Yes, not a problem. Okay, so again, if there is a T periodic signal, so someone told you that this signal, it has it satisfies this expression here for some big T. So this big T will take the name, the period of the signal. Then basically this signal is also periodic with a period that is equal to any non-zero integer multiple of big T. Okay, and the period can be negative. What is by definition positive is something called the fundamental period, which I will talk about shortly. Okay, so for the period itself, let's agree among us, we will allow some people actually put in the definition that the period is positive. We don't need this. And actually to go to multidimensional signals, we do not need this at all. So yes, we can allow the period to be something that is negative. If a signal satisfies x of t equal to x of t plus big T for every small t in R, then again replacing big T by any integer multiple will basically sustain the equality, and so any non-zero integer multiple of big T is a period. Zero is not a period because basically, again, the equation of the definition of periodicity is trivially satisfied if big T is equal to 0. We can actually say more, and this is also an important observation. What if you have a signal x of t, and then it has big T1 and T2 as periods? So someone told you have this nice signal, and actually x of t plus t1 is equal to x of t for every t in R. Moreover, x of small t plus big T2 is equal to x of t for every t in R. So basically our first statement tells you that T1 is a period. Our second statement tells you that T2 is a period, right? Then actually any integer combination of T1 and T2, so long as it's non-zero, is also a valid period. And you can check this, right? So if you do the check with taking T1 plus T2, so x of T1 plus T2. Remember that T2 is a period. T2 is a period means what? X of something plus T2, x of something plus T2, let's put it x of something plus T2 is equal to x of this thing, because T2 is a period. So basically this quantity here is equal to x of this thing here, which is T plus T1. But T1 itself is a period. So x of t, small t plus big T1 is x of t. So if T1 and T2 are periods, then T1 plus T2 is also a period. It will also satisfy the definition of periodicity. In fact, the definition will be satisfied for any integer combination of T1 and T2. Okay, so keep this in mind. Okay, so if big T is a period, any non-zero integer multiple is a period. No, not necessarily. I'm just saying it as a very general statement. As a very general statement, okay, that if T1 is a period, T2 is another period, so somehow you are sure that this is true and that this other statement is true, then it must be the case. It must be the case that basically that any non-zero integer combination of big T1 and big T2 is a period. we don't need to improve like the T2 itself is a multiple of T1 or something. Okay? So basically, to classify signals in a rigorous way, okay? We will see. We will see. I will actually talk about all possibilities right now. Okay? So to basically classify signals, okay, we will define this set psi. Okay, and so psi is basically the set of all big T's that are real numbers. And so we are allowing actually now big T to be equal to 0 for mathematical reasons that will be obvious shortly, such that x of t is equal to x of small t plus big T for every real small t. Okay, so now this set, which is psi, is guaranteed to be non-empty, right? Because we know that basically if you put big T equal to 0, then this will be true for all signals. Okay, so this set psi, it's guaranteed to be non-empty, right? Because it includes 0. 0 is there. 0 is there in this set psi. Okay. Now, this psi, again, it's the set of big T's that for which this inequality is true. We have 4 cases. What are the 4 cases? First case is the case in which psi only includes the number 0, nothing else. So there is no non-zero big T for which this is true. Okay, so this is the first situation, and this is the situation of aperiodic signals. So if psi only includes big T equal to 0, right, then, and there is no non-zero big T satisfying this, then our signal is not periodic, it is aperiodic. It may happen that actually psi is R, is the set of real numbers, which means that for every real number, this is true. Okay, so this happens for constant signals, constant continuous time signals, right? So if x of t is equal to 1 for every t, which is the signal that if you plot, it's like this, just a line 1 like this. Now, basically for this constant signal, x of t is equal to x of t plus big T for every big T you can think of, right? Because, the signal is simply constant signal, right? So in that case, psi will be the set of real numbers. And so you get the constant signals, and all those guys, they are periodic. Of course, a constant signal is periodic because actually this is satisfied for every basically big T, including all non-zero real numbers. So this is the first case of a periodic signal, which actually all real numbers are possible periods of the signal, and set psi is basically the set of real numbers. The third possibility is not intuitive. I will comment on it later. You can get as psi a dense proper subset of R. So a proper subset of R, it means something that is less than R. So it's not all elements of the set R, some of them. Okay, but what happens is that it should be a dense subset or a dense proper subset of R. Okay, and so dense, like basically the set of rational numbers. Okay, and basically so basically a dense set, again, it's like a set such that if you take any open interval on the real line, you will have at least one element in the set. So this is the third possibility, which is that psi is a dense proper subset of R. Okay, so basically there are periods here, and basically those signals for which a period is a number that is basically that belongs to a dense proper subset of R, those signals can be shown to be discontinuous everywhere. Okay? And what is an example of a signal that looks like this? So our friend, this signal. So of course this is periodic. Okay, so those guys are periodic. The only aperiodic case is the first case. Those guys are aperiodic. So signal, which is the indicator of T in Q. Okay, so remember, this is the signal that we talked about earlier in the course and said that this signal is equal to 0 almost everywhere. And so this is a signal that is 1 at the rational numbers, that is 0 on irrational numbers, and it is equal to 0 almost everywhere because it is not 0 on a set of measure 0. The rational numbers basically are a countably infinite set, and or countably infinite subsets of R are basically they have measure 0. And so basically the integral of this thing will give you the integral in the sense of Lebesgue is well defined and is equal to 0. Here is the claim. This signal here is indeed a periodic signal. Okay, and each rational, let's put it, each non-zero rational number is a period. Okay. Why is this? Okay, let's see. So suppose that you examine, so this is our x of t. Suppose that you examine x of t plus a rational number, non-zero rational number. Okay, so what is x of t if you add a rational number to t? Okay, so how can we find this? Okay, so basically x of t plus a rational number. Let's consider the two cases of small t. If t itself is a rational number, right? A rational number plus a rational number is a rational number, okay? And so basically this will be 1 if t is rational, right? Because irrational plus irrational is guaranteed to be rational, and basically the function is defined so that if its argument is rational, then it is equal to 1. Now, if t is irrational, then an irrational number plus a rational number is guaranteed to be irrational, right? Because you can do a proof by contradiction, right? Because if if you have an irrational number plus a rational number that is equal to a rational number, okay, so let's say that t plus r, and this is rational, is equal to c, which is rational, then on both sides you can subtract minus r, which is a rational number, and you get t is equal to c minus r, and a rational number minus a rational number is rational, so irrational equals rational does not make any sense. So basically, if t is irrational, you add a rational number, you get something irrational, and this function, when you evaluate it at irrational numbers, you get a 0 if t is irrational. And so what is this thing? So x of t plus a rational number is 1 if t is rational, 0 if t is irrational. Guess what? This is x of t itself, which is the indicator of t belongs to q. Right? So it means that any non-zero rational number is a period for this signal. Any non-zero rational, because if you basically evaluate the function at t plus some rational number, okay, then you will get x of t back. So all the rational numbers are basically periods. But irrational numbers are not periods. Irrational numbers are not periods, right? And why is this the case? So let's suppose that you examine x of basically minus square root 2, okay? And then you have the irrational number square root 2. Okay, so can this be a period? Can this be a period? No, because x of minus square root 2 plus square root 2 is not equal to x of minus square root of 2. Why is this? Because this guy is irrational, and so x of minus square root of 2 is equal to 0, but x of minus square root of 2 plus square root of 2, this is x of 0, which is 1, because 0 is a rational number. So the trick, why are the irrational numbers not periods? It's because the irrational numbers are not a field. You can sum two irrational numbers and get a rational number. So if you take a square root of 2 plus minus square root of 2, you get a rational number. So irrational plus rational is guaranteed to be rational, but if you sum two irrational numbers, the result may be irrational or rational. So because of this signal here, okay, which is, I mean, it's like impossible to plot, the signal is indeed a periodic signal. It is a periodic signal for which any non-zero rational number is a valid period, and no irrational number is a valid period. You can show any irrational number of your choice, and you can show that basically, x of t equal to x of t plus big T is violated at some small t on R. So in that case, the periods possible for this function constitute not all R like for constant functions, but a proper subset of R, and this proper subset of R has to be dense. So like the set of rational numbers. Okay, so this is an example of sort of a weird periodic signal, periodic continuous time signal, and yes, it is there. It's a signal that is nice, and because it's periodic, we can like do its Fourier series and stuff like this. Okay. Now the fourth possibility is that the set psi, again, remember what is the set psi? It's the set of all possibilities that satisfy the definition of periodicity, but we also allow 0, so that this set is guaranteed to be non-empty. So it always has the 0 in there. So basically, you can have a psi being basically the integer multiples of some strictly positive real number. So this is like the third type of periodic signals, and those are the signals for which big T, okay, in this case is P or minus P, 2P or minus 2P, and so on. And we call P the fundamental period of the signal. Now, for 2 and 3, basically there is no fundamental period. There is no fundamental period defined. Okay, so the fundamental period is a concept only if your periodic signal is here. So there is no fundamental period for constant signals. There is no fundamental period for those weird signals that are periodic and their periods belong to a dense proper subset of the real numbers. A fundamental period is basically for those signals that whose periods are the non-zero integer multiples of some strictly positive number. Okay, so this is the fourth case. Now I will say something, just to, why do we have just these 4 cases and so on? Actually, there is a fundamental mathematical result. Okay, so let me, just for your, for completeness, mention what actually is going on here. So set psi is an additive subgroup of the group of real numbers with the plus operation. What is this? What is this? So psi, of course, it is a subset of R because you define it to include values from R. So it is a subset of R. Okay. So here, that's the reason you use subgroup. It's a subset of R. It's an additive subgroup. Why is this? Because if T1 belongs to psi and T2 belongs to psi, it must be the case that T1 then T1 plus T2 belong to psi. So that's this idea that I discussed here. So psi defined as such is a subgroup, and if you are careful, you know why we actually allow 0 to be included, right? Because if the subgroup, you will need to include the identity element of addition, which is 0. Okay, so psi is an additive subgroup of basically R with the plus operation. So there is a theorem that any additive subgroup of R with plus operation is either, any additive subgroup is either discrete or dense. It's either discrete or dense. Okay, and the proof relies on the concept of infimum, finding the infimum of a certain set. Okay, so basically, it's I will not go into the details of this, but like those 4 cases are exactly what we have. We don't have any other cases, and basically this is like this itself is a mathematical result. We cannot have except that psi is the trivial subgroup containing only the identity element of addition. It can be the full set of real numbers, and this is basically for the periodic constant signals. It can be the multiples of some positive number, so these are the periodic signals with the fundamental period, and basically psi can be this weird thing. Most likely it is this thing that is maybe new for some of you, that basically psi can be a dense proper subset of R, and we have those signals that are like basically this guy here, which is a periodic signal, and all rational numbers, all non-zero rational numbers are proper basically periods, and the irrational numbers are basic periods. Okay, so basically this is something that is like an exhaustive classification, and it basically relies on this result that if you have an additive subgroup of R, it's either discrete or dense. Okay, so the discrete cases are basically cases 1 and 4. So those are the discrete cases. In the first case, you get just 1 point. Here we get basically the integer multiples of p, and the dense cases are basically 2 and 3. You can have the full of R, or you can have a proper subset of R, but it has to be dense. Okay, and why in this case x of t is discontinuous? I think you can show that if you have a signal, a continuous signal at a point. So if you have with x of t that is continuous at a point, and if its set of periods is a dense proper subset of R, you can show that actually your signal is a constant signal. Okay, so if you put here a signal that is continuous even at just 1 point, you can prove rigorously that basically this is constant everywhere. And so it's actually case 2, not case 3.